Hello viewers, how are you? Welcome to my channel Physics with Rams. So today we are going to discuss about surface tension and surface energy. Before going to start this topic, those who are new to my channel, please subscribe my channel so that you receive notifications regarding my channel, as well as you can clear your concepts regarding physics. Remember one thing, while learning the physics you have to analyze. As much as you analyze, you can understand the physics in a easy way. Let's start this topic, surface tension. So in this case we consider a container which is filled with liquid. So here, in order to represent this surface tension, we consider three molecules located at three different locations. Here, observe that when we consider this molecule, and let us consider it as A. Observe that due to cohesive force, it experiences a balanced force in all directions. So what is meant by cohesive force means the force of attraction between same type of molecules is known as a cohesive force, or we can also call it as a cohesion. Whereas the force acting between different types of molecules is known as adhesive force, or we can also call it as adhesion. In this case, we are representing that the force of attraction is acting between same type of molecules. So we can say it as a cohesive force. Observe that for molecule A, cohesive force is in equilibrium in all the directions. Whereas when we consider the molecule B, since it is somewhat lower within the liquid, it experiences a force of attraction in the downward direction. And some of the molecule force of attraction is due to air, so it will be dragged into the liquid. Whereas when we consider the third molecule, observe that the force of attraction on the molecule is due to water, liquid, as well as due to air. So when we neglect this air medium, because we are discussing about the cohesive force, so here what happens is it experiences the force in the downward direction. As it experiences the force in the downward direction, the molecule will be dragged in the downward direction, and since it is dragged in the downward direction, it stretches over the surface, because the molecule which is present within the liquid will not try to move in the upward direction. That's why the molecules which are on the surface will be stretched over the surface, just like a elastic membrane. This elastic membrane helps the insects or any other to walk on the liquid. The elastic membrane which is stretched on the surface is represented as surface tension, and this surface tension is represented by T. It is being represented by T, where surface tension is given as force acting per unit length. Force acting per unit length. So here we can also define this for surface tension as when we consider a liquid, the tangential force acting on both sides of a imaginary line drawn on the surface of a liquid is known as surface tension. Here we had drawn an imaginary line on the surface of the liquid. Observe that the force is acting towards this side as well as towards this side. That's why it is known as a tangential force. Observe that the tangential force acting on both sides along the imaginary line drawn on the surface of the liquid is known as a surface tension, and it is given as a F by L. So the unit for surface tension is Newton per meter in SI system, whereas in CGS system it is a dyne per centimeter. So here the dimensional formula for surface tension is m to the power of 1, L to the power of 0, T to the power of -2. Here this surface tension can be represented for different bodies, just like when we consider a wire which is floating on the surface of a liquid, then it experiences surface tension on both sides. So here if we consider the length of this wire is L, then the force acting based on the surface tension is given as F is equals to T into 2L, where 2L is the length. Since the tension is acting on both sides, we consider the length on both sides. So force acting on this wire is F is equals to T into 2L. Whereas similarly, if we consider a disc, here radius of the disc is R. The force acting due to the surface tension is given as F is equals to surface tension into circumference of this disc 2 pi R. Suppose if we consider a circular ring, due to surface tension, the force will be acting in the inward direction as well as the force will be acting in the outward direction. Then here the force in this case is given as F equals to surface tension into the radius of the ring is considered as R, then T into 2 into 2, nothing but 4 pi R. This represents the force acting in the case of a ring. Whereas in this way we can represent the force acting in the case of different bodies when they float on the surface due to surface tension. Similarly, if we consider a square of side A, the force acting on this square when it is floating on the surface of a liquid is given as F equals to T into perimeter of this square, nothing but 4A. Suppose if we consider a square which is made up of a wire, and if it is floating on the surface, then the force acting in this case can be given as T into, since the force will be acting on both sides, it can be represented as 8A. In this way we can represent the force based on surface tension in different cases. Take a screenshot, we will continue. Okay, let's observe this problem. A liquid is contained in a vertical tube of semicircular cross section. The contact angle is 0. Now we have to represent the ratio of forces based on surface tension on curved part as well as a flat part. So first of all we consider the semicircular tube. Observe that we had considered the semicircular tube. As you observe, the radius of this tube is represented as R. When we consider the curved part, the force in this case can be given in terms of surface tension as T into circumference of this curved part, nothing but pi r. Now, when we consider the flat part, let us consider it as C. When we consider the flat part, the force in this case is given based on this diameter. So, F is equal to 2 into r plus r, nothing but 2r. So, here we have to find the ratio of curved part to flat part. Then, F suffix C by F suffix L is equal to T into pi r by T into 2r. So, observe that r and T gets cancelled. Whereas, the ratio of forces for curved part to flat part is pi is to 2. Take a screenshot, we will continue. Observe the next problem. Find the maximum radius of a wire of length L and density rho such that it may not sink when it is floating on a liquid. So, suppose if you consider a wire is floating on a water. Now, we have to represent the maximum radius of the wire so that it may not sink within the water. For that, we can consider that the weight of the wire is equal to maximum force due to surface tension. So, here the maximum force in terms of surface tension is given as mg is equal to T into 2L. Whereas the mass is represented in terms of density. Why? Because here we had given the density. Observe that density equals mass by volume. Whereas mass is given as density into volume. Whereas density into, since it is a wire, area of the wire is represented in terms of radius as pi r square into height of the wire, nothing but L. So, as we substitute this in this equation, it can be represented as pi r square rho g L is equal to T into 2L. After that, 1L gets cancelled, and here r square is equal to 2t by pi rho g. So, here from this we get r is equal to under root of 2t by pi rho g. This represents maximum radius of the wire so that it may not sink within the liquid. We can also represent a maximum diameter. Why? Because we know that d max is equal to 2 into r max. So, when we bring this 2 inside the square root, it can be represented as 4. 4 into 2 is 8 t by pi rho g. This represents maximum diameter of the wire so that it may not sink within the liquid. Take a screenshot, we will continue. Now we are going to discuss about surface energy. So, here once again let us consider the container which is filled with the liquid. So, here once again let us consider two molecules A as well as C as we had seen in the previous case. So, since the molecule C is on the surface, it experiences the force in the downward direction due to cohesion. Due to cohesion, it experiences the force in the downward direction. Whereas, as it experiences a downward force, the molecule, the work has to be done on the molecule to stay on this surface. The amount of work done on the molecule to stay on the surface is known as potential energy. Why? Because the amount of work done on this molecule will be stored in the form of potential energy. Why? Because the molecule is not moving its position, its kinetic energy will be zero, so it has potential energy. As the surface area will be large, its potential energy will be large, it will be maximum. As the surface area is minimum, the number of molecules on the surface decreases, so its potential energy will be minimum. That's why as you observe that the molecule tries to attain a spherical shape. Why? Because a sphere will have less surface area as compared to different shapes. That's why we can represent that the water molecule or any molecule tries to attain or move in the form of a sphere. We can observe in our regular life. So here, as you consider this condition, in order to remain in the equilibrium, the liquid has to maintain a minimum potential energy. It has to maintain a minimum potential energy, then only it will be in equilibrium. It will be in equilibrium. So now based on this concept, we are going to define this surface energy. Surface energy is nothing but potential energy of molecules, or we can also call it as a potential energy of a molecular force. Potential energy of molecular force is equal to surface tension into area. So here from this we can represent the surface tension as a potential energy of a molecular force by unit area of a cross section. This represents a surface tension in terms of surface energy. Whereas in this case, the surface tension unit is represented as joule per meter square in SI system, and in CGS system it is represented as per centimeter square. So in this way we can represent the surface energy. We can also represent or derive the expression for surface energy by considering a U-shaped wire and a slider is present at this point. So here when we dip this U-shaped wire within the soap solution, a soap film will be formed on this wire. As the soap film is formed on this wire, since the wire is movable, it experiences the force in the inward direction, and the force acting in the inward direction is represented as a T into 12, surface tension into length of the wire. So this is the force acting on this wire, and it tries to move in the inward direction. Now in order to balance it, here a force has to be applied on the wire so that the wire will be in equilibrium. So now we had applied a force F such that it balances this force due to surface tension. So here if we increase the force such that the wire attains a new displacement, and this displacement is represented as X. Now the amount of work done in order to move the wire by applying an external force is given as W is equal to force into displacement X, whereas the force is represented as F is equal to T into 2L into X. So here observe that length into breadth, nothing but area, so it can be represented as T into A. From here the surface tension is given as work done per area. Already we had represented that the amount of work done is stored in the form of potential energy. So it is given as a potential energy per unit area, where potential energy is nothing but a potential energy due to molecular force per unit area represents a surface tension. So by using this concept, we can represent the amount of work done in different cases. Take a screenshot, we will continue. Now we are going to represent the amount of work done in different cases. Let us consider we had formed a liquid drop of radius r by doing a work done w. The amount of work done in this case to form a liquid drop is given as w equals to t into change in the area, nothing but A2 final area minus initial area, whereas initially the liquid is in the form of a flat surface. So here the area is neglected. Why? Because initially there is no liquid drop, and here T into final area is 4 pi r square. So the amount of work done in order to form a liquid drop is T into 4 pi r square. Similarly, when we consider the radius of the liquid drop has been increased from R1 to R2. R1 to R2. Then in this case the amount of work done is given as a surface tension into change in the area. Final area is given based on the radius R2 and initial area is given based on the radius R1. So it can be represented as a 4 pi into R2 square minus 4 pi into R1 square. So here as we take 4 pi as common, it can be represented as 4 pi t into R2 square minus R1 square. This represents the work done in this case of liquid drop when the radius has been changed from R1 to R2. Whereas similarly, when we consider a soap bubble has been formed with a radius r, then the amount of work done is represented as T into A2 minus A1, whereas area is represented based on the inside as well as outside. So it will be twice, then it can be represented as T into 2 into 4, 8 pi r square minus 0. So it can be represented as 8 pi r square t. Similarly, when the radius of the soap bubble has been increased from R1 to R2, then the amount of work done in this case can be represented as W equals to T into 8 pi R2 square minus 8 pi R1 square. Observe that here we can take 8 pi as common. As we take 8 pi as common, it can be represented as 8 pi t into R2 square minus R1 square. So this is the amount of work done in order to increase the radius of a soap bubble. Take a screenshot, we will continue. Observe a numerical. Find the work done when a liquid drop of radius capital R splits into n identical drops, each of radius small r. In terms of capital R as well as in terms of small r, we have to represent the work done. So here when we consider a drop of radius capital R, it splits into n identical drops, each of radius r. So here observe that the mass in both cases remains same. So the expression can be represented in terms of mass. So here when we consider the mass of this drop, it can be represented as a density into volume of this drop, nothing but 4 by 3 pi r cube. When we consider these identical drops, the mass in this case can be given as rho into n number of drops into volume of each drop 4 by 3 pi r cube, where r is the radius of each drop. So here when we equate both these expressions, observe that rho into 4 by 3 pi r cube is equal to rho into n into 4 by 3 pi r cube. So here 4 by 3 pi as well as rho gets cancelled. Observe that r cube is equal to n into r cube. From here r is equal to n to the power of 1 by 3 into r. This shows the relation between bigger drop and smaller drops. From here we can also represent small r is equal to, when we bring it towards the side, it can be represented as n to the power of minus 1 by 3 into r. Now let us represent the change in area, whereas a surface area is equal to final area minus initial area. Since it has been splitted, energy has to be supplied to this system so that it may split, whereas a final area can be represented as number of drops into volume of each drop 4 pi, area of each drop 4 pi r square minus area of the initial drop, nothing but 4 pi capital R square. So here when we take 4 pi as common, it can be represented as n r square minus r square. So here we have to represent the work done in terms of capital R. Observe that small r equals to n to the power of minus 1 by 3 into r. When we substitute this here, it can be represented four pi into n into the value of small r is r capital R square into n to the power of minus 2 by 3 minus r square. So here since bases are same, powers can be added. 1 minus 2 by 3, nothing but 3 minus 2 by 3, nothing but n to the power of 1 by 3 into r square minus r square. So here it can be given as 4 pi r square. Why? Because r square can be taken as common into n to the power of 1 by 3 minus 1. This represents surface area. Now the work done in terms of capital R is W equals to surface tension into area. So here surface tension T into area is 4 pi r square into n to the power of 1 by 3 minus 1. This is the amount of work done in terms of capital R. Similarly, we can represent the amount of work done in terms of small r, where observe that capital R equals to n to the power of 1 by 3 into r. As we substitute in this expression, the amount of work done can be given as T into 4 pi into, in the place of r, if we substitute n to the power of 1 by 3 into r, it can be represented as n to the power of 2 by 3 into r square into n to the power of 1 by 3 minus 1. So when we multiply this n to the power of 2 by 3 inside, then T into 4 pi r square. Observe that n to the power of 1 by 3 plus n to the power of 2 by 3. Why? Because bases are same, so powers can be added. 2 plus 1, nothing but 3 by 3, nothing but n minus n to the power of 2 by 3. So this is the expression for work done in terms of small r when a bigger drop is splitted up into smaller drops. We can also represent the expression in terms of volume. Observe that volume is given as V equals to 4 by 3 pi r cube, whereas we can represent this expression in terms of area. We know that 3v by r is equals to 4 pi r square. From this expression, 4 pi r square is nothing but area. As we substitute this in this expression in the case of work done, then observe that in the place of 4 pi r square we can substitute 3v by r. Then the work done is given as T into 3v by r into n to the power of 1 by 3 minus 1. So let's multiply this r inside. When we multiply, it can be represented as 3vt into n to the power of 1 by 3 by r minus 1 by r. So here observe that small r equals to n to the power of minus 1 by 3 into r. Then 1 by r equals to n to the power of 1 by 3 by r. So in the place of n to the power of 1 by 3 by r, we can substitute small r. So the expression is 3vt into 1 by r minus 1 by capital R. So this is the amount of work done in terms of smaller radius and capital radius, initial and final. Take a screenshot. Please give a like to this video, share this video to your friends, and don't forget to subscribe my channel.